This podcast is the first in the series on gases, gas behavior, a look at some of the properties of gases, and the kinetic molecular theory we use to explain their behavior. Physical characteristics of gases are well studied, and as you can see from this little animation, as the temperature increases, the volume increases. The graph shows a straight line. That's because the pressure is constant at 1.5. Notice that there are two green weights on the piston that's moving up and down. This kind of thing is what we're going to be studying in gases. We're also going to be studying the reasons behind it. The kinetic molecular theory has a series of assumptions, and we will use these in our study of gases. We're going to assume that gases consist of tiny little particles, either atoms or molecules, and that they're so small they're essentially volumeless. Not only are they volumeless, they're also in constant random motion colliding with the walls of the container, and those collisions are what cause the pressure. We'll also assume that the particles of the gas do not attract or repel each other, and that when they collide, those collisions are perfectly elastic and no energy is used up. And speaking of energy, you need to know that the average kinetic energy of the gas particles is directly proportional to the temperature of the gas, and in fact does not depend upon the identity of the gas. Some of the things about gases we need to know then is that gases will expand to fill their containers. They're a fluid, they flow. They also have a very low density, 1/1000th the density of the equivalent liquid or solid, and that they can be compressed. They also have properties of effusion and diffusion, which we'll explain in a little bit more detail. Diffusion describes the mixing of gases, and the rate of diffusion is the rate of the gases mixing, so that as you notice in the diagram, there is a barrier between the two different gases, the red and the gray ones. But once the barrier is removed, the gases all intermingle evenly on both sides to fill the entire container. This has implications later on. They also effuse, and effusion is a picky definition describing the passage of a gas into an evacuated or empty chamber through a tiny hole. It's actually how some measurements of gas properties are done. Pressure is the one thing that all gases exert, and you need to remember that it is caused by the collisions of the molecules or atoms with the walls of whatever contains the gas. It is equal to a force per unit area, and the units in SI are the Newton per square meter, which has been renamed the Pascal. A standard atmosphere, that is the weight, the pressure exerted by the atmosphere on this Earth at sea level, is 101,325 newtons per square meter. We often abbreviate that as 101.3 kilopascals. That standard atmosphere long ago was known as 1 atmosphere, which was equivalent to 760 millimeters of mercury. Hg is the symbol for mercury, which has also been called 760 torr, and you'll see why in a moment. Pressure was first measured by Evangelista Torricelli. He was an Italian scientist, and you can see where the torr comes from in naming them. He used a device called a barometer, and baro meaning weight, and meter meaning measure. That's where the name of the object comes from. His early barometer was a glass tube full of mercury that was inverted in a tub of mercury. Mercury is a liquid that is almost 14 times as dense as water. And so it turned out that the pressure of the atmosphere would support a column of mercury 760 millimeters high at sea level. Now, these barometers aren't much in existence anymore due to the hazard associated with mercury, but that is the early barometer. We also have a few other pressure items we need to be aware of. But as I said, standard pressure was 1 atmosphere or 760 torr. Standard temperature in gases is 0 degrees on the Celsius scale 273 on the Kelvin scale. And we will more often use the Kelvin scale with temperatures than anything. And it turns out that a mole of gas at 1 atmosphere pressure and 273 kelvins has a volume of 22.42 liters. And so we have defined the molar volume of an ideal gas at STP at 22.42 liters. And that will be a number you will need to remember. In subsequent podcasts, we're going to explore the relationships between pressure, temperature, volume, and the number of moles of gases in various situations.